Yes, so we are looking at some tube. This doesn't have to essentially be, doesn't have to be a circular, but just some contour which is a very thin tube. Okay, and I'll tell you what thin really means here in just a bit. So let's assume that this is the axis, and we are only looking at torques. The torque. Okay. Now, assume that there is some constant called r. It doesn't, as I said, it doesn't have to be the radius, but something which gives you how far the how it's an approximate measure of the distance of the wall of the tube from the center. Okay, and then let's say that t is the thickness. Okay, when you have r is much greater than t, that is that length scale associated with the radius is much greater than thickness t, this is when you will say that this is a thin walled tube. Okay, what's a good ratio? I don't know, maybe 10, 20 would be big enough. Okay, so only for those cases you'll use these formulas. Don't use it when R is comparable to T. So for a solid shaft, clearly it's not true because their T is 0. It's not true for a thick a shaft or hollow shaft, but as a uh, thick cylinder, it's not true. Okay, like the ones we've seen so far, the problems you couldn't write them as thin wall tubes because R was not much greater than T. Now we're trying to derive a formula for the torque and the shear stress due to this torque T. So we identify some element here. Okay, let's say that this is uh, some element. We take it. Take it out. This looks something like this. Okay, let's say that this part is B, this part is A. Okay, so since there's a torque, there's going to be a shear stress. Let's call that FB, FA. This is let's call this the Z direction. This is the Z direction. And this is basically where the thickness is. This is thickness. Okay, so let's write a formula for the net force in the Z direction. It's going to be, let's say, FA minus FB, just from the figure there. FA is going to be TA times, so force is shear stress times the cross-sectional area. So we'll assume that this thickness is, see, so this length, let's call this is dz or delta z. It's along z. And then we'll assume that this thickness, which I wrote down here, is TA for the lefts for A and TB for B. So it's T times TA times delta Z. Okay, so when I say this thickness, basically also this thickness is TA, right? This part. This part is also TA. And then that part is TB. So force times shear stress times the cross-section area will give you the force. And that's why that formula And then same thing can be written of B, which is tau B, TB, oh, sorry, thickness B times delta Z. Okay, but the net force is 0. So we can write tau A EA equals tau B TB. Or in other words, if you take tau and you multiply with T, you get a constant. Okay, so that's one insight, that is, it's a constant. Okay, now once we have that, we can now go ahead and derive a formula for how the torque T is related to tau. For this, I would draw the cross section in the thin shell. Okay, let's consider a small element of, let's call that ds. So ds is arc length. It's subject to torque. So let's put the torque here. As a result of this torque, this is going to have a shear stress of tau. And as we said earlier, this is the thickness T. So we want to compute the force. The force is simply the torque times dA. What is dA? dA is the area here. So ds is the torque. So the area, this cross-sectional area is ds, which is the arc length, which is along this direction, times the thickness. Okay, so the torque is, definition is, it's a moment, r times df. Clearly, r is this is r. Okay, so r df, df is tau ds times t. I'm going to pull out everything which is a constant. So r is a constant, the shear stress is a constant. With r, sorry, r varies with, sorry, my bad, r varies with distance, right? So there's an r here, and then here there'll be a different r, so I can't really pull it out. I could remove t out, though thickness is constant, so r ds. Okay, now this is something which we can compute. Okay, for that, well, let's just write it down. First, let me write it down and explain to you why it's 2 times a. Okay, so it's 2 times a, and bear with me, I'll tell you why it's that 2 is coming there. But what this a signifies is this. If you have the shell, what you do is you take the midpoint, the midline, okay, and then this area from the midline, so the area within the dashed line, which is the midpoint, is actually a. This is the area enclosed by the median line. So it's the dashed line. Okay, that's basically this integral r ds is that area, twice that area. Okay, now the question is, why is there 2 coming? Why is it not just a? So this we can figure out from in this fashion. So y2. So if you have an element, let's call that ts. This is r. Let's just say this is ts. Okay. Now we want this area. This is r, this is ds. So this is like the area of a triangle. Let's just call this a. Let me put a bar here. This is because this is the area of not the complete one, but only of a small section. So this area is what? Area of a triangle, which is half base, which is ds, times height r. Then move this, move it here. Okay. So when you move this around, you have 2a bar is r ds. And so when you take the integral of this whole thing, you get the yellow part, which is shown here, and then you get a twice of a just because it's the area of a triangle. Okay, but we have now got the formula for the torque. So from this formula, we can write tau is T divided by 2 times TA. And we can also, which is something I've not derived, theta is T times L divided by 4G A square T. So here is the shear stress. Here's the angle of twist.